Hello, everybody, and welcome to the final lab of the semester. So this semester, we're going to finish off looking at your pet molecule. So major premise behind this lab is that we're going to be giving you an unknown liquid solvent. So this is the exact same procedure we have to follow if somebody left a mysterious unlabeled beaker of a clear colorless liquid out in the lab. We have to figure out what the heck it is so we know how to properly dispose of it. In this case, we are going to give you one of 13 different unknowns. Your job is to figure out which one it is. So you're going to identify your unknown using 4 separate tests. So the first of which is going to be the one we've seen the most of the last couple of weeks, and that is IR spectra. So you're going to actually perform this one yourself, and this is going to provide information about what functional groups are present or absent. So look for alcohols, look for carbonyls, look for carboxylic acids. A lot of these functional groups we've helped show you so far. Then we've got NMR. So NMR tells you a lot of information about the relative position and location of groups. If I know I have a carbonyl, where are my CH groups or where are my hydrogens with respect to this? This will help you really build up the full molecular structure, which can help you identify nearly identical compounds like 1-butanol versus 2-butanol. Then we're going to go ahead and use GC. So GC can help evaluate the relative size and polarity of an unknown. So this is going to be pretty much a cousin to the thin layer chromatography that we started off the semester with. And the final test is going to be solubility. So this is going to also provide us a lot of information about intermolecular forces as well as size. Because as we've seen repeatedly throughout the lab this semester, different different molecules, really based on their shape and functional group, I'd expect to have different solubilities in different mixtures. So when we put all 4 of these together, you should be able to conclusively identify which one of these species you have. So one of the first ones we're going to deal with is IR spectroscopy. So some of you have had a chance to run IR before. Even if you haven't, this is a different technique. So previously we were trying to collect IRs of solid samples. This week we're going to be working with a liquid sample. So how we're going to do this is you are going to first of all check with me that the IR is free, because we only have so many sample salt plates we can use to run our samples. So once you've checked with me that it's okay, you can start preparing your sample for an IR spectra. And you're going to add a drop or 2 of your unknown to a salt plate. So these are nice clear salt plates that will not show up in the IR region or in the IR spectra, thus making them perfect as sample mounts. You're going to put them together as a sandwich with your sample in between, so you don't want too much sample. A drop is usually more than enough. And then you're going to place them in a sample holder, at which point we can then shoot our IR beam through the sample. And again, much like a UV vis, figure out where the absorbance is located, and using the knowledge that we've seen previously, be able to figure out what functional groups are present. So I'm going to go ahead, either me or the TA is going to show you how to collect the spectra. And using that, you can go ahead and save your spectra, identify your peaks, and use this for your analysis. Once you're done, you're going to lightly rinse those salt plates with acetone to remove any excess sample. Then you're going to lightly dry with a chem wipe so that you're not scratching the cell or leaving any lint. And then you're going to place it back in a desiccator, because these are salt plates, meaning that they will dissolve in the presence of water. So be very careful handling them. Then you're going to either want to bring a phone so you can take a photo of your spectra, or a flash drive so you can directly download it from the computer so you have an image to analyze later if need be. The other major spectra technique we're going to be using is NMR. So you've had the chance to see NMR spectra before. This time you're going to be able to collect an NMR spectra of your own. So you're going to work with it with either me or one of the TAs to collect this spectra. You're going to go ahead, take an NMR tube and put 1 or 2 drops of your sample into a clean NMR tube. And the best way to do this is often going to be with a pipette. If you have issues getting it down, just let me know. Then we're going to fill that NMR tube with a solvent that does not contain any protons, so it won't show up with the NMR. And you're going to typically fill it to a height of about 2 to 3 fingers high. There is an exact line showing you how high to fill it on the waste hood, so you can use this as a good reference point. Any lower, and you won't be able than 2 fingers, and you won't be able to get a good spectra. Any higher than 3, your sample may either come out too dilute, or you might just be wasting a very expensive solvent. Then you're going to want to place this in a beaker, or preferably an Erlenmeyer, for transport, so you can walk it down into the basement so that you can go ahead and follow either mine or a TA's instructors, or your TAs, where they will guide you through how to collect the spectra. And we will go ahead and then once you're done, you're going to go ahead and empty your NMR tube into a halogenated waste, not the aqueous waste. This is a very specific organic halogenated waste reserved for our chloroform sample. And your NMR spectra is going to be saved into a Google Drive, which you can then go ahead and access later if you need more details. The next major method we're going to be using is gas chromatography. So gas chromatography, lo and behold, is another type of chromatography, and it works by injecting a small amount of a volatile liquid, so it will quickly evaporate into a column filled with fast-flowing air. So we are going to regularly be blowing air, in this case atmospheric air, through a metal column or through a silica column that we can then run past the detector. So the walls of the column are going to be made of a nonpolar silicone polymer. So we've got a nonpolar stationary phase, but the big one, as opposed to the polar one in TLC, this means that larger nonpolar compounds are going to travel slower. In comparison, smaller compounds are going to be more volatile, and so they should travel a little faster as they will evaporate in that low pressure of flowing gas. We can also speed up this process by heating the sample. So the gas our GCs will also act as heaters to push the sample through at a regular interval. So as the samples are moving through the tube, samples that have a stronger interaction with that tube walls are going to move slower. So again, larger nonpolar molecules, the more nonpolar IMF, or the more intermolecular forces I can build to a nonpolar surface, the slower it moves. So this means that molecules that can form larger dipole-induced dipole and induced dipole, also known as dispersion interactions, will move slower. So this will mostly focus on size, but there's going to be a couple surprises in the trends based on the relative polarizability of the molecules involved. So a detector is placed at the end of this column, and it will release an electrical signal, which we will read in millivolts, when a sample hits the detector. So each of these detections are presented as a chromatogram. So you should see a spike when an individual sample goes through. So if I have a sample that contains multiple components, I should expect multiple spikes. Most of your samples should be pure, so should contain only a single spike. Though do let the sample run till you make sure it returns completely to baseline. You will base your measurements based on the peak signal, so where it hits essentially the highest height. And you're going to measure the amount of time it took to get to that peak. This is known as the retention time. However, because we're measuring these samples based on retention time, it makes it very important that you start collecting that spectra the moment you inject the sample. This often means that this can take 3 hands. So if you need to work with somebody else where you'll inject the sample, well, they hit the start button. That works just fine. And again, full details of how to do sample injection and runs are present in your lab manual, and I'll be going over some of the highlights in lab. Now, an important feature is if the GC conditions are kept constant. So if you use the exact conditions we specified in the manual, the retention times and general peak shape for each sample should be relatively constant. And we uploaded GC retention times for all of the unknowns on Canvas. So you're going to want to consult the Canvas retention times, which will also be present in lab, to go ahead and see where your retention time matches best with the one provided. So this can help us narrow down our possible unknowns by comparing what unknowns have a sample retention time similar to yours. Something to be cautious about, though, is based on the ambient conditions any given day, how long the sample had been running, and how accurate you are at injecting the sample and hitting start at the same time, mean there might be mild differences. You could get better agreements if you ran all of the unknowns yourself. But because we're working from essentially quote unquote literature values, they can differ by up to a minute. However, this means that you can typically reduce the number of possible unknowns from something like 13 now to about 3 or 4. And then using the other 3 techniques, this can be a huge help in identifying what your likely unknown is. The final test that we're going to be performing is to test the solubility of your unknown. So we've seen this in multiple of our different labs. Structures of a molecule will dictate what solvents it can dissolve in. This has been a major feature we've used to help separate samples using separatory funnels. But we can also run this in reverse. If I know what solvents it dissolves in, I can help identify the relative size and polarity and functional groups located on the molecule. For example, if a molecule dissolves in water, I know it's either relatively polar or relatively small. As the molecule gets larger and more nonpolar, it's less likely to dissolve in water. Similarly enough, if it dissolves in acid, it likely contains this means it can likely be protonated and contain something like an amine. If it dissolves in a base, it means it likely contains a acid functional group, which then again will make it ionizable. Very similar to the trends we've used to help separate molecules by acidifying or increasing the pH of a sample to help separate in between an organic and aqueous phase. So we're going to test this trend by dissolving 2 to 3 drops of your unknown in up to 3 milliliters of a series of different solvents. So we're going to do this by slowly increasing the amount of solvent that we've added to our sample by about a half a milliliter at a time to figure out if your unknown is slightly soluble in each of these conditions or very soluble. If it dissolves immediately, we're probably looking at very soluble. If it poorly dissolves, it's likely only slightly soluble if it takes that full 3 milliliters. Now, we're going to test a variety of different mixtures, including neutral water, basic aqueous conditions, slightly basic aqueous conditions, acidic aqueous conditions, and slightly acidic. So this will help us identify our functional groups. And we can do this by walking through a flowchart available on Canvas, where you start by testing the solubility in water. If it's soluble, based on the pH, we know if it's more likely to contain an acid group or a base group. Then we can see if it dissolves in base. Depending on the strength of base, we can figure out the size of the strength of the acid. Then we can try and dissolve it in various acids. Based on how soluble, it will tell us how easily it is to protonate. Very easy, like an amine, or much harder, like an oxygen-containing functional group, such as an alcohol, ether, aldehyde, any of our carbonyl-containing species. If you put it in concentrated sulfuric acid and I can throw a proton on it, I probably will. If it doesn't dissolve in any of these, well, that means I'm looking at something with no nitrogens, no oxygens, meaning either an alkane an aromatic, or an alkyl halide. So using these techniques, we can identify our species. So before we go ahead and start, always a good idea to review the relevant chapters. So I'd highly encourage you to take a quick overview of chapter 19, which is on GC, and reviewing chapter 22 on NMR. We're hitting this one pretty hard. As well as make sure to read the lab manual for experiment 9. And again, reviewed the appendices on 7 and 8, so IR and NMR. This time, I want you to read slightly different information. There is some information on how to perform and run the samples. So for chapter 7, we are running a liquid sample, so follow those directions. For chapter 7, these NMR instructions are for the smaller NMR that we have up in the main lab. We will use this if we run out of time, but the instructions on how to prepare the NMR tube are still pretty good. Then make sure to read the files on Canvas for GC retention times and our solubility flowchart, and try and include this information in your lab manual. It will make determining your results much easier. Hey, congratulations, you're already watching this video. And then make sure to write the pre-lab notebook, including all of this information, specifically the procedures from the lab manual, both appendices, specifically 7, and again, the GC retention times and that solubility flow chart. So again, there's a lot of procedural information in these manuals that I'm not covering here. I highly encourage you use it. Make sure you answer the questions to consider. Then in lab, as usual, we're going to meet in the chemistry lounge. I'm going to do the safety overview this time. And then we're going to enter the lab and check to see what stations are available. I will likely start by doing a quick overview of how to use the GCs before you can go ahead and move through all of the other stations. By preference, try and perform the following tests if it is available. NMR, we can only run 2 to 3 students at a time, and it's going to take about 10 to 15 minutes per. So we're going to start early, and it's going to be running all lab. This might be the thing that takes the longest. Collect your IR spectra. So for that, you're going to have to work with me over on the IR, and only do either of these in conjunction with the TA or instructor. Then make sure to perform the GC analysis. After you've received instruction, you can do this on your own, and determine your unknown solubility. This one you can run entirely on your own, and if you need to, you can leave it off in the middle if you have a chance to run the other ones. And again, because we're working with larger classes, I'll try to push you through these as fast as I can. Then you're going to fill out your pet molecule worksheet as you go, which I will provide when you show up to lab. And when you have collected all of your other data, go ahead and ask the instructor or TA for the molecular formula of your compound. You're going to use this to help draw your structure, determine your IHD, and identify your species. If you have already finished it, you can go ahead, you can then use all this information to complete your worksheet. If you have a chance, you can turn this in at the end of lab. Otherwise, it's just due at the beginning of the next lab, which is going to be all the way on the week of December 2nd. So as you're going through, keep an eye out to see what equipment is available. Make sure to follow all guidance on the instrument use. Some of these instruments are very expensive and very finicky. If you have any questions, please check with an instructor or TA before you do anything. And again, similar to that, we're going to be using syringes with needles to inject our GC samples. These are very sensitive and easy to break. And make sure to keep those IR cell plates away from any sources of water. This means you might need to switch into a new fresh pair of gloves if you've been handling any aqueous samples. And again, pay very careful attention to the volume of your NMR tubes. And when you are done, make sure to rinse with acetone and shake dry to try and dry it out as much as possible so that the next lab can use them. And again, make sure to take careful observations on those solubility tests, especially because unless you have practice, it can be really hard to see the separation between 2 immiscible layers. So if there is a layer in between your sample and the water, this can be hard to observe. If you have having a hard time seeing this, go ahead and add an extra drop or two of your unknown if you're unsure. If you still don't see 2 layers form, you're probably missable. And then when you're done, go ahead and clean up. And that's more or less the lab. So wrap up for this one is mostly make sure you do your post-lab scans. This means you should be writing everything in your notebook as you go and fill out your pet molecule worksheet so that you can do it at the beginning of lab checkout. Which brings me to week of December 2nd. That is going to be lab checkout. You will be checking out of your drawers. You will be cleaning up the lab. You will be making sure that we leave everything in a better shape than we found it. And again, everybody's expected to check out. If you do not, you will be charged money. And you will also be charged for any missing glassware. So as you're going through this through lab this week, make sure that you have everything in your drawer. All right, that's a wrap, and I'm looking forward to seeing everybody in lab. Until then, take care.